Hello everyone, please let me know if I am completely audible and visible. Anyone in the comment section? Uh, Please just drop a comment if I am completely visible and audible and my screen is visible to you. Anyone? Drop a comment either yes or no so that we can start. Anyone, please drop in a comment either yes or no. Okay, so I am starting. The today's topic is the 2D prefix sum. So in the last lecture we were talking about the prerequisites and the primitive structures that fails so that we need the advanced data structures, and in that series we were talking about the prefix structures, and in the last lecture we have discussed about the single like 1D prefix sums and the 1D prefix XORs. So there we have talked about the 1D prefix structures. 1D prefix structures. And we have talked about the prefix sum, the product, and the XOR. So these three we have already seen because they are simple to implement. We can just apply the simple prefix structure uh, in these type of queries and we can just query a solution. But it is not always the case. We have also discussed two bitwise cases that are the special cases. So we have discussed about these special cases in which uh, we have to discuss about the and or operations. Now these and or operators are say operations. These bitwise operations are not say associative. You cannot directly write like this: and of L to R is equals to the prefix structure we have created R bitwise and prefix of L minus 1. We cannot and here we can use OR also if the query is for OR. So we cannot directly write this. This is wrong because these two operations are not associative in these terms. We cannot directly apply the prefix structure, but we can do a special case here. We can handle this case if we are talking about in terms of bits. Okay, so suppose let us first look at the AND operation. AND operation. By AND operation I mean bitwise AND. So now suppose if I am given two integers a and b, and if I am writing the binary forms of these a and b, like I am converting this a into its binary representation and this b into its binary representation, and then in that case there could be four cases. These are the four cases. uh, so these are the corresponding bits. Okay, now if the corresponding bits of both the integers are 0, we are going to get 0 as a result. If the corresponding bits are 0 and 1, we are going to get 0 as a result if it is an AND operation, bitwise AND operation. If it is 1 and 0, we are going to get 0 here, but if both the bits are set, then we are going to get 1. So now from this table what we can conclude? So the conclusion is, if all the bits if all the corresponding bits of the participating integers are set, then in the result of the bitwise AND operation we are going to get a set bit. And if any of the corresponding bit in the participating integers, like here we have only seen two, it can be many like a, b, c, d. So if any of the corresponding bits that of any participating integer is 0, so that bit would result as 0 in the resultant. So that we have to we have to remember these are the conclusions. If all the bits are set, then we are going to get a set bit, and if any of them is 0, we are going to get a 0 here. Now let us talk about one kind of problem, and the problem is similar to the problem we have discussed yesterday in the last lecture. The problem is we are given a query like and L to R, and before that we are given an array, and this array contains n elements. This array contains n elements. Okay, and suppose it is zero based indexing. Now this L and LR query um, wants me to calculate the bitwise AND of all the integers from L to R, like AL bitwise AND of AL plus 1, bitwise AND of AL plus 2, all the way till bitwise AND of AR. So this is something we want to calculate, and we have already discussed that we cannot directly write this, but what we can do is we can go in the bit representation, in the binary representation of these integers, we can go in the binary representation of these integers, and there we can represent it in the prefix structures. So how we are going to do this, let us see. Okay, so this thing I need. So suppose if all the integers, like if a is the array, then all the ai is suppose less than equals to 10 to the power 6. In that case, we can represent all the AIs using 20 bits only. Now suppose if this is my array, if this is my array, 3, 4 and 5. These are the indices 0, 1, 2, 3, 4 and 5. These are the indices. Now every index is storing some integer. Say for example, say this is a0, this is a1, this is a2, this is a3, this is a4, this is a5. Now we can represent each of the integers using these 20 bits. Now suppose we are representing it just by using 5 bits, just for the understanding purpose. 1, 2, 3, 4 and 5. Now suppose this a1, a0, this a0 is represented by using these 4 bits 0, 1, 2, 3, and some of them would be set, some of them would not. Okay, so like these are the numbers, consider these as your numbers. Okay, so these are the binary representation of your numbers. Now what we can do, for each of for each bit we can traverse and we can prepare the prefix structure, a 2D prefix structure. We can prepare a 2D prefix structure here in for each bit, and for each bit we can calculate this prefix sum. And what the prefix sum is storing at the ith index, the sum of all the elements from 0th index to ith index. So this is what the prefix I is storing. So at third index, suppose if I am talking about the 0th bit, at third index it would be storing the sum of all the set bits, all the bits that is set at the third index. So this is how we are going to we are going to do the prefix query on the bits, because we can represent each integer in its binary form, and then we can prepare the prefix structure on the bits. Now how it is useful? How it is useful? So we have already concluded that if all the bits in the AND operation are set, then and then only the corresponding bit in the resultant would be set, otherwise it would be 0 or unset. So in that case, suppose if I am given a query, with a query that is AND L to R, like we have to take the bitwise AND from L to R in this array. So suppose if this is my L and if this is my R, what I'm going to do is I'm going to calculate the prefix sum of the 0th bit, and if I'm going to calculate the sum that falls in this L to R range, and that is nothing but prefix R minus prefix L minus 1. So yes, this is how we are going to get the prefix sum of this 0th bit. Now if this sum is equals to R minus L plus 1, that means all the participating integers has this bit as set, then in the resultant we are going to make this bit as set, otherwise we are going to make this bit as unset. So this is what we are going to do here. So for every bit, like in 20 bits we can cover all the numbers which is less than equals to 10 to the power 6. So we are going to move for all the 20 bits, and we are going to calculate uh, the prefix sum of each bit. And if all the bits are if the prefix sum is equals to this, that means all the bits that are participating are set, then we are going to make that particular bit set in the resultant, otherwise not. So in that way we can create the result of this query. Now what would be the time complexity? What would be the time complexity? So for time complexity, when we are using the simple prefix structure, there we are achieving O of 1 time complexity to process each query. But this is not the case in the AND or OR operation, because here we have to go we have to traverse for 20 times to get the result, because we have to check all the bits. So in that case the time complexity to process each query is log of n to the base 10. So that is the time complexity for querying for processing each query. Now if we are given q queries, then we are going to get the time complexity as order of q into log of n to the base 10. Now if this q is comparable to n, in that case we are going to get the time complexity as order of n log n to the base 10. So this was the special case that we left in the last lecture. So this is how we are doing for the AND operation. We can follow the similar procedure for OR operation. we can follow this similar process for OR operation also. But in the OR operation, what we need is, like in the OR operation, if you see, the corresponding bits are like this. If both the bits are unset, we are going to get 0. If this is the case, we are going to get 1. If this is the case, we are going to get 1. And if this is the case, we are also going to get the 1. Now, if all the bits are 0, then and then only we are going to get a 0 in the resultant. Otherwise, we are going to get 1. So in that case, what you have to check? In that case, we have to check if the prefix sum we are calculating on L to R is giving me a 0 as a result, then for that bit the resultant bit would be unset, and for all the other cases, either it is 1 2 3 whatever, we are going to get uh, a set bit for that corresponding bit, and we'll be adding this bit as a set bit in the resultant. So this is how we can do the query for OR operations. So now we are done with these two special cases. Now let us start with the topic that we have to cover today, that is 2D prefix sum. 2D prefix sum. Okay, so for this 2D prefix sum, first we must know what is a 1D prefix sum, that we have already discussed in the last lecture. Now what we are storing at the ith index in the 1D prefix sum. So suppose if 0 1 2 3 4 5 6, these are my indices, and suppose if I am talking about, and this is my prefix array. Now if I am talking about the prefix 4, now what this prefix 4 would be storing? It is storing the sum of all the elements from the 0th index till the 4th index. So this is what the prefix, the 1D prefix sum means. Now what would be the 2D prefix sum? So let us discuss that too. Suppose if we are given a grid or a 2D matrix of n cross m, in that case, if we are talking about the 2D prefix structure or say 2D prefix sum, in that case, every cell, like if I am talking about the prefix of ij, here we have created a 2D prefix. So suppose if I am talking about the prefix of ij, so this prefix of ij would be storing the sum of complete rectangular submatrix that ends at I comma jth point. Okay, so this prefix ij is storing the sum of the complete rectangular submatrix that ends at the ijth point. So suppose if I am talking about this ijth point, now what this ijth point, the prefix of ijth point would be storing? So it is storing the sum of okay, so it is storing the sum of all the elements that falls in this rectangular complete submatrix, because this is the complete rectangular submatrix that ends at this point. There may be many matrix that can end at this point, like this could be a submatrix that ends at this point, this could be a submatrix that ends at this point, but we are talking about the complete submatrix. So this is the complete submatrix that ends at this point. So this value, this particular value is storing the sum of all the elements which falls in this particular submatrix. Now how it is going to be useful for us, or how we are going to say maintain or create a prefix structure on the 2D matrix, let us discuss that. Okay, now how we are going to store the prefix structure and the 2D prefix sum in the given grid. So let us discuss about that too. So suppose if some grid was given to you and now you are creating a prefix grid. So this is your prefix grid. The size is the same, n cross m. You're given an grid and you are preparing the prefix grid on that. Now suppose if you are at any random element, now if you are at this point, now what do you want? That this element should store all the sum of all the elements from this point to this and this element. Now how can we achieve this? So suppose if I'm talking about this prefix ij. Now suppose if I'm saying I am adding prefix of I minus 1 j, okay, now suppose we would be having some value, suppose a is the matrix that is given to you. So this aij would be referring to the value that is present at this cell. So suppose if I am adding prefix of I minus 1 j in this element, then what is going to happen? So the prefix I minus 1 j would be this value, and this value would be storing the sum of all these elements, and we have added this element also in this value. Now only thing that is left to be added is this one. Now how can we add this one? So suppose along with this, along with adding this, I am also adding prefix I of j minus 1. If I am also adding this element, so this is the cell I am referring to in the prefix structure. Now this would be storing all the elements which falls in this rectangular submatrix. So if you see, we have added this submatrix, then we have added this submatrix with this element. So now we have the sum of the submatrix we require, but here we have done something wrong, that is we have added the sum of this submatrix twice. So one time we have to subtract this. So suppose if we are subtracting this particular value, that is prefix of I minus 1 j minus 1 from the thing whatever we have added till now, we would be getting the result we want. So we would subtract this thing, prefix I minus 1, because we have added it twice. So this is how we are going to create our 2D prefix sum. This we can use for creation. This query we can use for the creation of 2D prefix sum. Now suppose if we have created this 2D prefix sum, now how we are going to query on that prefix sum? Okay, now suppose if we have already created this 2D prefix structure, if we have already created this 2D prefix structure, this is n cross m, and now if I am giving you 2 points, that is x and y, or say not x and y, because this we are going to refer as coordinate. Suppose if I am giving you 2 points, that is p point with x1 y1 as the coordinate and q as the x2 y2. Now if I want to calculate the sum of p as the left corner, uh, top left corner, and q as the bottom right corner, then how we are going to calculate the sum of this um, submatrix? So suppose if this is the point p, if this is the point p, and if this is the point q, now if this is the point p is the top left corner of the submatrix, and the point q is the bottom right corner of the submatrix, then that means we are referring to this submatrix. Now if we are talking about this submatrix, now if we are talking about this submatrix, and suppose if I am asking you to calculate the sum of all the elements that falls in this submatrix, then what we can do is, so for the nice solution, or say brute force approach, what we can do is, we can start traversing from this point, and we can traverse all the elements which falls in this submatrix, and we can calculate the sum of this one. So for processing each query in the naive way, or in this way, we would be requiring, what would be the time complexity? The time complexity for processing each query would be O of n square, because in the worst case this p point can be at the starting and the q point can be at the ending. For that we would have to refer all the elements that falls in the complete grid. So in that case the time complexity for processing this query would be O of n square. But using the prefix structure, if we are using the prefix structure, then we can achieve a time complexity of O of 1. Now how we can query in this? How we can query there? So now suppose if I am talking about querying in the prefix grid structure. So let us talk about the query. How we are going to query there? So for query, this, if I am referring to this point, that is prefix of x2 y2. So if I am talking about the prefix of x2 y2, that means this point. So this point would be storing all the sum of all the elements which falls in this submatrix. But first thing we want to subtract is the sum of this submatrix. So for that what we can do is, we can subtract prefix of, here the number of row has been changed, and as this, for this the number of row is x1, so this would be x1 minus 1. So that would be x1 minus 1, and the column would be, as this column is referring to this one, and this one is nothing but this y2, so that would be y2. So now we have subtracted this particular set of values. Now we have to, after that we have to subtract this set of values. So for this, for subtracting this set of values, we can just subtract this particular point. We can just subtract this particular point in the prefix structure, and this particular point is nothing but uh, the row would be x2 and the column would be y1 minus 1. So that is prefix of x2 y1 minus 1. So we have to subtract that too. So that would be minus prefix of x2 y1 minus 1. Now if you see, we have subtracted this particular submatrix 2 times. So now we have to add this in the prefix structure because it has been subtracted twice. So that would be adding prefix of x1 minus 1 y1 minus 1. So this is how we are going to query on the prefix structure. So we have seen two things. This particular method is to store the prefix structure, and this particular method is to query on the prefix structure. Now this is all for today, and like what we have to discuss today. So the theory part is complete. Now let us take a problem on that, what we have studied till now. So this is the problem. The problem statement is very simple. We are given a 2D matrix M. M is the name of the 2D matrix that we are given with, and the dimensions is R into C. R is equivalent to N and C is equivalent to M, that is number of rows and the number of columns, and find the maximum subarray in it. So we have to find the maximum rectangular submatrix, or we can say that we have to find a rectangular submatrix which contains the maximum sum. So we have to return that sum. Okay, so let me explain you the problem statement. So the problem says that we are given a matrix, a 2D matrix, just like this one. So we are having lot of elements that is present in each cell of this grid. Now we have to this particular grid can have many number of subgrids, like this is a submatrix, like this is a submatrix, and this could contain the different sums. So we have to select the submatrix which contains the maximum sum, and we have to return that maximum sum. Okay, so suppose if this submatrix is the submatrix which is containing the maximum sum, so we have to return the sum of all the elements which falls in this submatrix. Okay, now the naive way to do this is what is the naive way of solving this problem? What is the naive way of solving this problem? So what would be the naive way of solving this problem? So the naive way would be, we can put our first endpoint here, and then we can traverse for our all the way for our second endpoint. and when our second endpoint is fixed, we can then calculate the sum of that submatrix and we can compare it with the maximum value till now. But what would be the time complexity of this? So let us calculate the time complexity of the nice solution. So what would be the time complexity of this solution? So for the time complexity, suppose if we are trying to set our first point, so we are having n square different ways to set. Okay, suppose this is n and this is m. So now what would be the, say, the number of ways we can put our first pointer? So we can put our first pointer anywhere in this grid. So that would be n cross m. So this is the number of ways we can put our second pointer. Now the number of ways we can put our second pointer is again n into m. So that would be again n into m to putting up the second pointer. Now suppose if we have put our second pointer here. Now to calculate the sum, again we have to move uh, to the n into, like, in the worst case we have to move to n into m elements. So that is again n into m. So that is what the time complexity is. So if m is comparable to n, this comes out to be order of n to the power 6 as a time complexity. Now can we reduce it? Can we reduce it? Or can we use a better approach of doing this? So yes, we can use the prefix sum. We can use the 2D prefix sum. So suppose if we are using the 2D prefix sum, then what we can do? So in that case, if we have set our first endpoint, if we have set our second endpoint, then instead of taking the sum, we can just do the prefix query on that, and we can calculate in just order of one time the sum of this submatrix in just order of one time. So for that, uh, so for that, this n into m factor would be reduced. So we don't need that in this case. So the time complexity reduced to order of n to the power 4. So now let us look at the constraints. So if you look at the constraints here, the constraints for R and C is 500. So the constraint here for R and C is 500. Now n to the power 4 of 500 would be like 5 into 10 square of the power 4. So that would be 10 to the power 8 and 5 to the power 4. So the 5 to the power 3 is 125, and so that would be 625. 625 into 10 to the power 8, that is nothing but 6 into 10 to the power 10, and that is definitely not going to run in 1 second. So this would give us TLE, that is time limit exceeded. So if we are going to, like, if we are going to write the solution using the prefix, if we are going to write the solution using the prefix sum, 2D prefix sum here, we are going to get TLE, because this is not the constraint which can run in the 1 second. So now what we have to do here, we have to search for some smart solution. We can type this as a code, but that would be waste of time, because I am pretty sure that this solution would give me TLE. Okay, so let us think for some smart solution. Can we do it in much better way? So this was the order of n square time, n to the power 4 time complexity. If we are able to reduce it in order of n cube, that means we are, in that case, that would be 5 into 10 to the power 2, and the cube of all this would be 10 to the power 6, and that is nothing but 5 cube 125, and that would be 1 into 10 to the power 8. So that we can do definitely in that time complexity. We can, and this time complexity would can run in one, not in 1 second but in 2 seconds, and we will be definitely given and the time for this would be 2 seconds definitely, because otherwise we cannot run it. And as you can see in the expected time complexity, we are required to do it in order of r into r into c. That is, again, if c is comparable to r, that would be order of r cube. So we have to do it in order of n cube time. So this would work. Now how we can do this? So if you have any doubt till now, whatever we have discussed, whatever we have studied, please ask. Otherwise we are shifting to the new topic here, because to solve this problem we require one more topic, that is Cadance algorithm, that we are going to discuss. Anyone having any doubts, please mention in the comment. Okay, so as we are not getting any doubts, we can proceed further. Now forget about this problem for a time being, and we'll be coming to this problem after a while. But before that, let us talk about the Cadance algorithm. Now what is the Cadance algorithm? Now what is the Cadance algorithm? So in the Cadance algorithm, like suppose if I am giving you a problem and the problem statement says you are given an array. The array can also contain the negative values. So we are given an array with the integers, and now I am asking you to calculate the maximum subarray sum. Now what do we mean by maximum subarray sum? So for this array there can be maximum there can be several number of subarrays. So which subarray is giving me the maximum sum? We have to select that subarray, and then we have to calculate the sum for that subarray, and we have to return that sum. So this is what I am asking, the maximum subarray sum. Okay, so for that this Cadance algorithm is used. So there can be several ways. Again, you can do this in naive solution. You can use the naive solution. You can put anywhere your first pointer, and then you can put anywhere as your second pointer, and this too would behave as your endpoints for the subarray, and then you can calculate the sum of this particular subarray, and then you can compare it with the maximum value, and you would be getting the solution. That is definitely one thing you could do. But for that, if you see the time complexity for that, if you are talking about the time complexity for that, what would be the time complexity here? So for moving your first pointer, for fixing your first pointer, you would require order of n time. Then for moving your second pointer, you would require again order of n time. And then for taking the sum of these values, you would be requiring order of n time. So this would be O of n cube. But now suppose if you are taking the prefix sum, or if you are like while traversing also, like if you fixed your first pointer here, and then you are fixing second pointer here, then here, then here, and if you are calculating the sum along with moving the pointer, then you can achieve a order of n square time complexity. So this is the best time complexity you can achieve if you are using the naive solution, or if you are using this two pointer method. But we can do it in just order of n time if we are using the Cadance algorithm. Now what is the Cadance algorithm? Let us discuss that. Okay, and the catch is here we are also allowed to take empty subarray. Okay, so this is the catch. Now suppose if this was my given array, these are the indices like A0, A1, A2, A3, A4, A5. All these are my elements. So now suppose if I am taking the sum, I am starting from the 0th index, and if I am taking the sum at any point, like first I would be taking the sum of A0, then I would be adding A1 to this, then I would be adding A2 to this, then I would be adding A3 to this. So at any point, if my sum becomes less than 0, now if the sum is negative, in that case, that this cannot be a solution anywhere, because this negative sum, if I am after that, suppose if I stopped here and the sum from this point, the sum from this point to this particular point is less than 0, that means it is, if it is negative, now if I am adding this sum to any sum further, like any sum after that, this is going to decrease something from this sum. So this is always disadvantageous. So if I am getting any sum less than 0, so this is always disadvantageous to me. This is always disadvantageous, and we don't want this thing to happen. So if this is the case, it is always better to take empty subarray. It is always better to take empty subarray, and we can just make our sum. If we are calculating the sum, so the sum variable is calculating this sum, and if at any point this sum becomes less than 0, then it is always better to take this empty subarray, and the sum of this empty subarray would be 0. So if at any point this sum falls below 0, we'll be marking us sum as 0, and then we are again going to increase the subarray sum at every point of time, and if again this thing we encounter this condition, we would be again changing our sum to 0, because in that case it would be always better to take the empty subarray. Now at every point we will be also comparing this sum with a maximum variable, and at last this maximum variable would be storing the maximum subarray sum. Okay, so how we can do this? So we can take a for loop from I to n, and we can just calculate, we can take a sum variable, we can initialize it with 0, and then we can just add this. Suppose ai is the given array, we can just add this ai value to this, and if at any point this sum becomes less than 0, we are going to take the empty subarray. That means we are going to make the sum as 0, and otherwise we have this maximum variable mx is my maximum variable, which we have already declared earlier, and we are going to compare this maximum variable always with this maximum sum, with this sum, to get the maximum value if at any point I want this maximum value. So if you calculate, if you try to like, so this, and at last we will be returning this maximum variable. Okay, that would be return max, and this max would be storing the maximum subarray sum. So this would be storing the maximum subarray sum. Okay, now if we try to calculate the time complexity of this thing, if we try to calculate the time complexity of this thing, now what would be the time complexity of this one? So suppose if we are talking about the time complexity, so here you can see that we are traversing every element only a single time. We are we are traversing from the very first point, we are adding it, and if it falls less than 0, we are making a sum 0. Otherwise we are moving to the next point, we are adding this, then we are adding this, and we are moving. So we are traversing the complete array only a single time. So the time complexity of doing this would be order of n. So now we can get the using this Cadance algorithm. So this is what the Cadance algorithm is. Now this is the Cadance algorithm. Using this Cadance algorithm, we can get the maximum subarray sum in just order of n time. So now this particular algorithm we are going to use to solve our previous problem, that is this problem, maximum sum rectangle. Okay, so now what was the problem? The problem was we are given a matrix. The problem was we are given a matrix. This was the matrix. So we are given a matrix and we have to calculate the so this matrix, like just like subarray, we can have a submatrix in this particular matrix, and we have to calculate the maximum sum of this submatrix. Like we can have a lot of submatrix in this given grid, and we have to calculate the we have to find this submatrix which is containing the maximum sum. Okay, so now how we are going, we have discussed how we are going to use the Cadance algorithms in the 1D array. Now we are going to discuss how we can use this Cadance algorithm in this to calculate this submatrix sum, maximum submatrix sum. Okay, so we have used this Cadance algorithm we have used this Cadance algorithm to calculate the maximum subarray sum of 1D array in order of n time. Now we are going to use this Cadance algorithm to calculate the maximum subgrid or say submatrix sum of 2D array or say 2D matrix and in order of n cube time. So that is the best time complexity we could ever achieve to calculate this particular thing. Okay, so now this was our given submatrix and this was given grid. This was our given grid. Okay, and now suppose so the given matrix was M, and now suppose if I have stored what I have stored, so like if this was my given matrix, and now if I have stored the prefix sum of each row the prefix sum, so if I have stored the prefix sum of each row of each individual row um, in the prefix matrix so this is our prefix matrix. So now I have stored the prefix sum of each row in the prefix matrix. So that means if I am referring prefix of ij, this has stored, so if I am referring this value, this has stored the sum of all the elements starting from the zeroth in like for the ith row, I am storing the sum of all the elements that falls in this index range. Okay, in this index range, this j. Okay, so suppose if I am take two examples. If I am saying prefix 1 4 and if I am saying prefix 2 3, so the prefix 1 to 4 means go to the 1th row, and this 1th row I'm talking about the sum of this 0th index, this 1st index, the 2nd index, 3rd index, 4th index. I am talking about this sum. that is the sum of all the elements that falls in the first row from the index 0 to the index 4. Now if I am talking about, say, this query, so what is happening in this query? So in this query we are saying go to the second row, and this prefix 2 3 would be storing the sum of all the elements that falls in the second row from 0 to third index. Like this is 0 index, this is 1 index, this is 2, this is third. So I am talking about this on the sum of all the elements which falls in this range. Okay, so this we have stored in the prefix of ij. Like we have calculated this prefix, we have created this prefix array, and we have stored this here. Now what we can do is, using order of n square time, we can fix our left and right pointer. So we can put our left pointer here, say, and right pointer anywhere in this point, and now we can calculate the sub array sum of each row of all the elements that falls in this range. And now this complete sum would behave as a single element, say ARR. So this ARR 0 is say this ARR 0 is the sum of all the elements which falls in this left to right range in the 0th row, and then ARR 1 would be storing the sum of all the elements which falls in this range for the first row, like from left to right, which falls in this first row, and this would be my ARR 1. Now suppose if I am talking about ARR 2, in the ARR 2 I am visiting the second row, and in the second row I would be calculating the sum of all the elements from this left to right segment. Now this complete sum is behaving as my this element as a single element. Now this ARR 0, ARR 1, ARR 2, all the way till ARR whatever the row number is, and this is behaving as my 1D array. Now what I can do is, I can put my I can like this is going to behave as 1D array. Now I can apply the Cadance algorithm in this 1D array to get the sum, to get the maximum subarray sum, and this is how we can calculate and the Cadance algorithm, and this is the way how we can calculate the maximum subarray sum in the 2D array. Okay, now after some time you would be say increasing your right pointer, and the right pointer would be pointing this point, and then you are again going to create this array. Now the array 0 would be storing the sum of this thing, and the array 1 would be calculating this array and the sum of this thing, and then the sum of this thing, and then you can again run the Cadance algorithm on this, and you can get your solution. Okay, so this is the idea. So to fix the left and the right pointer, we require the order of n square time, and to run the Cadance on that, we require the n time. So that would be order of n square into n, that is order of n cube time. So this is the time complexity I am talking about. So I think the idea is clear to everyone. So if you have any doubts in the idea we have discussed till now, please let me know in the comment section, and if you don't, then if you don't have any doubt, we can proceed to the code section, and we are going to code this particular solution because this is the final solution. And doubts? So as we are not getting any doubts, we can proceed to solve this particular problem. So this R and C is the number of rows and the number of columns, and this is the 2D vector, this M is the 2D vector. Okay, now we are going to create a 2D vector. So first we are going to create a 2D vector. Okay, Okay, so first we are going to calculate this, we are going to prepare this prefix array to calculate the prefix sum on each row. So for that we have declared this 2D vector, and then we can traverse all the way or for all the elements, and we can calculate the values that is present at each cell in this prefix array. So the prefix of ij would be the sum of the element that is present at this point, that would be m I minus 1. Why I am writing I minus 1 and j minus 1? Because the array that is the 2D vector that is given to us is 0 based indexed, and the prefix structure we are going to create is 1 based indexed. So that's why this thing. And then we are going to add the prefix I minus 1 jth value and the prefix I j minus 1th value, and now one value would be duplicated, so we have to subtract that. That is prefix I minus 1 j minus 1. Now my prefix, but here I don't need this thing because I'm just preparing the prefix array for a complete row. So we can just do this thing, prefix I j minus 1 plus m I minus 1. Okay, so why I've done this? Because here we don't need to create the 2D prefix sum, but we need to create the 1D prefix sum on each row. So prefix prefix ij minus 1 plus m I minus 1 j minus 1. So this would create the prefix on each row, and let us take a variable that to compare the maximum value, and initially we have initialized it with the minimum possible value of the integer, and then we will be setting up our left and right pointer. So int left equals to 1, and here we have to traverse it for the cth, because the left and the right pointer would be having a boundary as c, not r. R would be the number of rows. Left, and here this thing should be the capital C. Now we have fixed our left and the right pointer. Now let us calculate the array value, like arr value, and that is the prefix. For that, first we have to traverse for all the rows 1, that should be the capital 1, and for all the rows first we have calculate the value of arr, that is nothing but prefix of the ith row and the right value minus prefix ith row and the left minus 1. So that would be the ARR value, and we'll be adding it in a sum value that is going to be doing the job of the Cadance algorithm, and we will be adding this, and then we'll be comparing this thing with the maximum value for finding the max sum. Okay, and if at any point this sum is less than 0, we have to make a sum as 0. Okay, and then first thing we have to do is, we haven't declared the sum yet, so here we have to declare a sum. Let us int sum is equals to 0. So we have to declare a sum here, and after this is checking the maximum value of the sum, so we don't have to do anything. And after this point, I think we are in the main function. Okay, now this is the function from where we have to return the maximum value. Okay, so now we have done everything. Let me check if everything is fine. So we have created a prefix array of r plus 1 and c plus 1 value. All the values are initialized with 0. Then we have traversed from all the way from 1 to r and then 1 to c, and then prefix ij would be prefix I j minus 1 plus or minus. Okay, this thing is correct. Now we have declared a maxwell value to compare the maximum value with the int, and we have initialized with the minimum possible value of the integer, and then we have fixed our left pointer nested with fixing our right pointer. Then we have declared this sum equals to 0, and here we are running the Cadance algorithm. Okay, prefix I right minus prefix sum plus equals to r, and then here we are checking the maximum, and okay, so everything looks fine to me. Let me check the solution. Okay, so what was the okay, so my solution is giving 29. What was the expected solution? So the expected solution, okay, so here the expected solution is 29, so we are getting the correct result. Let us check if this solution works. Okay, so this was the correct solution. So this is how we can solve it. So we have talked about the nice solution, which we can do in order of n to the power 6 as a time complexity, and then we have reduced it to the order of n to the power 4 using the 2D prefix sum. Then we have taken the 1D prefix sum on each row, and then we have applied the Cadance algorithm, and that have reduced the time complexity through the order of n cube time. So this is all for today's lecture, and this is the complete prerequisite we have to do, or we needed to start with the advanced data structures. And in the next lectures we would be starting with some techniques of the advanced data structures. So this is all for today's lecture. Thank you.